Welcome to Pomodoro Joe for Sunday, July 9th, 2023. Today we're looking at LeetCode problem 2272, substring with largest variance. This is a hard problem. The variance of a string is defined as the largest difference between the number of occurrences of any two characters present in the string. So that's just saying the variance is the maximum character count minus the minimum character count of any two characters in the string. Note the two characters may or may not be the same. It's a little weird, but okay. Given a string S consisting of lowercase English letters only, return the largest variance possible among all the substrings of S. Ooh, this suddenly got interesting. A substring is a contiguous sequence of characters within a string. All right, so for example, we have AAB, ABBB. So our substrings are just A and AA and AAB and AABA, okay? And then you can also start here and just have AB or ABA or blah, blah, blah. So every single combination of these characters, as long as they're contiguous, you can't pick and choose. You can't like jump around or have gaps. All right, so it looks like for this, we could have 4 B's with 1 A. This would be my guess, so probably a variance of 3. And yes, we have a variance of 3. All right, and then this one, a little more complicated, A, B, C, D, E. This is a variance of 0 because they're all 1 count. All right. Okay, so with this, we'll put 25 minutes on the Pomodoro timer and get started. All right. So this is one of those problems where it helps to have some background. It helps to have some previous knowledge. And the previous knowledge we need for this one is Cadon's algorithm. Cadon's algorithm is a way to find the greatest or the maximum subarray sum. So the idea in Cadon's algorithm, let's see if we could give an example here. Let's say you have some array, 1, 2, 3, or let's say 1, 2, 4, 6, 8. And you want to find the maximum subarray sum. Now all of the subarrays are positive, so you just sum the entire array. That's your maximum subarray sum. Let's actually simplify this a bit. Let's go back to this. So you have 1, 2, 4. All right, let's do this. This is a good example. So we're trying to find the maximum subarray sum. So in this case, since all the values are positive, then the entire array will be the maximum value. 1 plus 2 plus 4 plus 6. Great, we got 13. That's our maximum. Now what if we do this? Now all of a sudden this changes. So 1 plus 2 is 3, but then you go down by 4. So now you're at -1. So if you add that to 6, you actually end up at 5. Which is less than if you just grab 6 by itself. So how do we go about solving this one in a very straightforward manner? Well, we use Cadon's algorithm. So in Cadon's algorithm, you go through every element, you keep track of your maximum, so 1 plus 2 is 3, then you get to 4. Now you have a negative value. Now if you were to continue, you could start with -1 and continue through the rest of the array. But we already know that -1 puts us at a disadvantage. It would be better just to declare bankruptcy, reset to 0, and start over. So as soon as you drop below 0, you just throw out that previous maximum and you start over. You basically start at 0 and you start doing your sum from there. So we'll be doing the same thing, but with letters. So the question is, how do we adapt that algorithm to work with lowercase letters? And the answer is, we can go through, do our sum, do our counts for letters, but these are just total counts. These aren't going to give us this positive or negative value. They're always going to be positive values or 0. So at what point do we do this declare bankruptcy and reset? Well, the idea here is actually to have the difference between 2 characters. So we just look at 2 different characters, compare their counts. Then when we have a comparative count of 0 or less, then we can reset, declare our bankruptcy, and restart our counting. So let's do that here. So if we can do this with just 2 characters at a time, what does that mean? Well, that basically means we have to go through every possible pairing of our characters. We have to do A and B, A and C, A and D, and then we have to do B and C, B and D. We have to go through every possible character pairing. All right, so let's just do this. Start our result at 0, and we will return our result at the end. All right, now we have some letters, and we'll just go through from A to Z. All right, so these are all of our letters. Now we'll go through every pairing. So we go A and pair it with B, C, D, E, so on and so forth. And then we go B, C, D, E. So we're looking for some maximum letter and some minimum letter. So for every, we'll call this the max letter index. So this is going to be the one that we're going to try to maximize while we try to minimize the other letter index. All right, so we go for every maximum letter index in our range and for every min letter index. All right, now you'll note I am going through the entire range both times because sometimes I want A to be the max, or I'll start with A being the max, and the next time I'll have B be the max, but I still want to catch A as the minimum. So we have to go through the entire range. But we don't need to count if it's the same letter. If we have A and A, we don't need to count that. So the first thing we'll do here is just remove that possibility. So let's see, we'll have our max letter. That's just going to be letters at max index. Here, let me give some space here. Our min letter. Actually, we can do it this way. All right, so if we have the same letter for our max and min letters, we can just continue. All right. Next, we'll grab our max letter and our min letter, and we'll have our min letter count and our max letter count. And now we have to go through every letter in our input string. So for letter, in S. All right, if this letter is our max letter, then we'll increment our count. If it's min letter, we'll increment that count. And if it's neither the max or the min letter, then we can just continue because we can ignore that letter. All right, so we're going through every letter in our input string. We're incrementing our max letter counts and our min letter counts. And if we have some letter that's not either the max or the min letter, we'll just continue. Now outside here, if we did update our count, what do we want to do? Well, let's check to see first, what's the delta between our max and our min? All right, if our maximum letter count minus our minimum letter count is less than 0, this is the point where we can declare bankruptcy and reset. So we have more of our minimum count letters than our maximum count letters. So let's just throw out that substring and restart. You know, I'm going to change these names. I'm just going to call it max count and min count. It'll be easier to read. All right, so we're declaring bankruptcy. We're just going to start over, and our min count is also equal to 0. Otherwise, at this point, our max count is greater than our min count, greater than or equal to our min count. We'll just recalculate our result. That's going to be the maximum of our current result, or this delta. All right, so this is looking pretty good, but there's a couple things that we're missing. Now, the main thing that we're missing here is we actually can't just take the max count if the min count is 0. So if we don't actually have any of these min letters, we can't just count this. We actually have to have at least one other count of that other letter. So one thing we might have to do out here, the min count is equal to 0. We'll just continue. We can't update our result if we don't have any of this min count letter. All right, so that's one problem that we run into. What's the other problem? The other problem that we'll run into here still has to do with this min count equals 0. Let's say we go through, we do count some min count at some point. Let's say we get min count, let's say we get our min count character first. That's actually a good one. Let's say we get our min count character first. So we have one min count, but then our max count is 0. So we found our minimum character first, we'll subtract 1 from 0. It's -1, so we declare bankruptcy, we reset. Then let's say we get a whole bunch of our max count, 1, 2, 3, 4, 5, 6, 7. Well, our min count is always 0. So at this point, we'll early out because our min count is always 0, even though we're getting a bunch of our max count, and there had been one min count at some point. We reset it when we did this declare bankruptcy. So we kind of need to keep track of whether or not we've ever seen our min count character. So let's add another value out here. So now if we've never seen our min letter, we'll return. This will be false. As soon as we see this min letter, then we know we have at least 1. So maybe I should do this. And then as soon as we see it, we'll say this is true. All right, if we've never seen our min character, we'll set this to false. Let's see, we still might end up having this minus this min count, and the min count could be 0, but we don't want that. We want this to be at least 1. So one thought is we could just set this to 1 here, but that's not really what we want because we might not want to start having a 1 count. We might find another minimum letter later on in our array. So we still want to start this at 0. We could do something here where if we had a min count, then this min count would be at least 1. Let's try that actually. We could try that. I'm not 100% sure if this is going to work. So if our min count at this point was 0, then we'll just set it to 1. So we basically look back in time that we did find at least 1 of these letters. But that might not work because if we look back in time, we might be passing, no, that could work. No, I think that might be okay. All right, let's just give this a try and see how it goes. We are off by 1. All right. I think it might be this guy. Let's do this a little bit more explicitly. Let's just go back to our basics. All right. So in here, if the min count is 0, we'll just continue. All right. So if the min count was 0, we'll move on. Great. All right. At some point when we exit, if we had some maximum count, but we never got a min count, so we're skipping all these min count zeros, but we do reset the min count every time we go negative in our delta. So at some point we might have a min count. We might have had a min count letter at some point, but we never passed this point. How do I describe this? Okay, in the situation where you run across your min count letter first, your min letter first, then this will always reset to 0 because you didn't have any max count characters. So you hit your min count letter first, this gets reset, then you basically skip all of this because every single time your min count's going to be 0 because you reset it inside of here. But if we ever run across this min count letter, that means there's at least one option. We know there's at least one subarray as long as we have some max count letter as well that includes both that max count letter and this min count. All right, so we need some correction out here. This is kind of ugly, but it's all right. If our min count, let's see, if we saw our min count letter, all right, so if we ever did find that min count letter, and we do have some max count that's greater than 0 here. It has to be greater than 1 because we need the delta to be greater than 0. So if we did at least see our min letter at some point. We currently have some max count that's greater than 1, so the delta will be greater than 0. And let's see, our min count has to be equal to 0 basically at this point because we did the reset. Then we can update our result. Oh man, this is super ugly. And this will just be max count minus 1 because we're basically subtracting the 1 that we did see, even though it might have been way back in our array. All right, let's try this. Okay, so this works. It's super ugly, but it seems to work. Well, let's submit it. Oh, yeah, let's submit this. I see an optimization we can do, but let's submit this to see if we can pass. And we pass, and we do pretty well, actually. So for this, we beat 69% for runtime and 25% for memory. That's not bad. All right, the optimization that I saw. We don't necessarily know we have all these letters in our input string. So what if we just go through the letters that we know we have? And that would just be a list of the set of all the letters in S. All right, so this might save us a little bit. Let's find out. Oh, wow, that saves us a lot. Holy smokes. Now we're at 92% for runtime and 25% for memory. So that's a huge savings. Sweet. All right, again, this is a variation on the Kadan algorithm for finding the maximum subarray sum. This is finding basically the maximum subarray delta between any two characters. So we actually have to go through every combination of pairs of characters in our input string. We'll just find the deltas between those characters by keeping track of our max character and our min character. Then when we ever run across a negative delta, we just do a reset and start over. This has some weird edge cases that we do have to consider, so that's where this bit comes in. Just keeping track of whether or not there are min and max characters in this entire string. If there was some min somewhere in the string, then we should at least have some delta. All right, well, we are low on time. I know this one's confusing, but definitely check it out. It's worth trying. All right, hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.